Hi, this is Math 8, Unit 4, Lesson 11, called On Both of the Lines. We kind of started getting a little bit of this in our last lesson where things would be on both lines. We talked about having two graphs and having a point that would be a part of both those lines where the two lines come together, if you're doing a coordinate grid or something like that. So first we began with a notice and wonder thing, looking at some bugs passing in the night, and we noticed that they start on different sides of the line here, and as time goes on they're moving at different rates. And so what happens when you look at this first bug, or right there, again looking at the front of the bug, this ladybug has gone 1, 2, 3, 4, 5, 6, 7, 8 little clicks, whatever that is, 8 units in 2 seconds, whereas the ant here, right, has gone from here, we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 in 2 seconds, right? And so for the ladybug, we know it's traveling, we could say things like it's traveling at a rate of 8 units per 2 seconds, or traveling at a rate of 4 to 1. Okay, over here the ant is going at 6 to 2 or 8 to 1. Okay, and we can see that continues there. There's going to be a point here as this guy goes that way and that one goes this way, where they're going to cross each other, right? They're going to pass each other at some point where they're going to be in the same place and say hello and move on. We look at the next one here, we can see the ladybug is still moving ahead, right? And it's still moving at the same rate. Here's, 8 more clicks have gone. And there it is there. There's her 8 more. And the ant, though, has moved from here all the way to now being off the thing or on the far side. And so they pass somewhere between these 2 seconds here. They pass there. And when you get to the last one, this one here, there's no ant at all. He's off the page somewhere and has gone away. That, or maybe he was squished by a giant foot, who knows. But the ant is no longer there and the ladybug is there. So we could say things like, for our ladybug, we know that it's going about a rate about 4 units every 1 second. The ant seems to be going about 8 units every 1 second. It's going a lot faster than the ladybug is, and it meets at some point somewhere between 2 and 3 seconds is going to be the place where they meet, right? Between 2 and 3 seconds, because after 4 they pass each other, and before 2 they haven't. So somewhere in there, hard to say what it is right now, but that's kind of the idea behind what we're going to look at today. Where do these things meet together? So here's a different ant and ladybug graph, and it says they're a certain distance apart and they start walking toward each other. The graph shows the ladybug's distance from its starting point. So I'm just going to make a little label here to say this is ladybug. From the starting point. It started here at 0, and it's going to go all the way this way. We can see that after 6 seconds it reaches a distance of 24 centimeters, right? So if I think about a number line like last time, it's like here's 0 and we're going all the way to 24, and it's going to take 5 seconds to get all the way to that point for the ladybug. The graph shows some starting point time and the label point 2.5 comma 10, which is right here, 2.5 comma 10 is when the ant and the ladybug pass each other. Okay, so at this point here, we don't have the ant's graph, that's where they pass each other. Okay, so this part where they pass each other, we're talking about the other line. Okay, we don't have the other line in our graph, we only have one. But there should be another line here for the ant, right? That's just missing. And that ant line is going to go through this point. Now we don't know where it's going to go at this point, but we know there's another line, and somehow there's going to be a line that goes through that point right there that shows when the ant and the ladybug are going to meet, when they're going to pass. It says that the ant down below is walking 2 centimeters per second. And that's the ant, going 2 centimeters per second. So let's look at this guy right here. If we know, for example, that this is a point on our graph, we know that it's going to go 2 centimeters every second. Okay. Now again, it's walking in a different direction from the other one. So we're going to be doing just so we can think about this here. We're going to be doing going down. Okay, a negative slope. Now the reason we're going to say negative slope is because they're moving in opposite directions. Okay, the ladybug is moving this way, and our ant is moving that way. And so we're going to say it's going to go down. So our graph should go like like this kind of thing, going down in a negative direction. So if the ant's walking 2 centimeters per second, we can kind of figure out, well, here is a distance of 1 centimeter and 2 centimeters is here, and if I'm going to go out to another second. A second in this case here is represented by 2 movements over, because it's a half for each one. And so I can actually plot off some points by going down 2 over 2, and I can say this is going to be the movement of the ant. In the same way, I could also look and say, well, this is going to go this direction here. We're going to go up 2 over 2 and up 2 over 2 here, and continue that way. If you notice, it's not just up 2 over 2 or down 2 over 2. If I went negative 2 and 2, that can reduce to negative 1 over 1. So really, I can connect all the dots here and say I'm moving down 1 over 1. I'm going 1 centimeter every half a second is what's happening in this case here. So it looks something along these lines, like so, for our ant. It says to write an equation representing the relationship between the ant's distance from the ladybug's starting point and the amount of time that has passed. Okay, so what we're saying here is let's write an equation that shows what's going on for the ant. Alright, well, our ant, we know from what we're looking at our graph here, our ant is going at a rate, what seems to be, it's going at a rate of 2 units, 2 centimeters every 1 second, right? So it's going to be going down 2 units every 1 second. Now, from the starting point though, we have to look at where it started. In our case, based upon our graph, we're starting right here at 15. So we could say that our equation is going to be y equals negative 2x plus 15. That's our starting point there. Now, if you weren't sure about this 15, there are some other ways to go about figuring that part out. Okay? Let's take a look at how we could do that here. Now, we know that's going 2 meters per second, and it gets right there. So if it's going 2 meters every second, I can take the 2 meters and I can multiply it by this point, which we have at 2.5. At 2.5, we know that it's gone 2 times 2.5, it's gone 5 meters. No, centimeters. Now the reason we know it's gone 5 centimeters is because it's walking 2 centimeters every second. And at this point, 2.5 seconds, that's where the ant is going to be. So if I take this x value and I plug it in here and multiply it by 2 centimeters per second, the rate, it tells me that the ant went 5 centimeters in 2.5 seconds. Okay? So if it's located at 10, which it is, I just need to take the 10 and add back in the 5 to get a starting point, which is right there. There's my 10 plus 5 to get there. So that's where this 15 comes from. So I went about just showing you how you could graph it and figure that out, but you could also do math to kind of go this way to say, oh, that's how you get the 15 there. Couple different ways to go about getting the starting point. So it's up to you what do you kind of see first to figure that part out. If you haven't already draw the graph of your equation on the same coordinate plane, which we've already done that there, and it's located there. I think the key thing is figuring out for the ant, just trying to graph that out to say what's actually taking place. That 2 centimeters every second, just graphing it out helps you see visually what's going on from one unit to the next. Let's take a look at the next one. It says Elena and Jada were racing 100 meters on their bikes. Both races started at the same time and rode at a constant speed. So same time and constant speed. Here's a table that gives information about Jada's bike race. So we can see that time from the start, 6 seconds, she'd gone 36 meters. If we wanted to use our constant proportionality idea, we could do 36 divided by 6. Remember, here's our x and our y from before. 36 divided by 6 means she's going at a rate of 6 meters per second. All right? Here, if we do 54 divided by 9, it is a constant speed. We can verify this is also 6 meters per second. That's what we know so far. It says graph the relationship between distance and time for Jada's bike race. So let's put time down here, and we're going to put our distance over here. And time, we're going to go ahead and count by 1, 2, 3, 4, 5, 6, 7, 8, 9. And for our distance, we're going to go ahead and count by tens. just so you have enough space on our graph to do this. I got it to 54. We know that at 6 seconds, she's gone 36. So we're going to go 6 and up to 36, which is about here. And at 9, we're at 54. So maybe we're about here. And we know we started at 0 because there was no time and she'd gone no distance. And so our graph would look something like that. Oops, I'll probably make a little straight line be a little better to use. So there's our nice little graph. And we have a graph that looks something like that. Okay, so it says that Elena traveled the entire race at a steady pace of 6 meters per second. On the same set of axes, graph the relationship between the distance and time for Elena's bike race. Now her rate, it says for Elena, is 6 meters per second. Well, what did we discover up above? Jada's rate was at 6 meters per second. Since those two are the same, 6 meters per second, 6 meters per second, that means that Elena's graph would be the identical graph on the same line. Okay? It's identical. Or we could say it's the same. However you want to say that, it's the same thing. So in terms of who won the race, there isn't a winner. We would say it was a tie. And it's going to be a tie because they're both going at the same rate. They start at the same time and went the same distance, and so they're going to be equal to each other. Okay? And that's what happens there. All right. So, is there a place where the two graphs cross each other? They don't really cross each other because they have the same points all the way along. So there's a zillion places where they are solutions to each other. Okay? So, looking at our summary here, it says that a solution to an equation corresponds to points on the graph, on its graph. That's what a solution is going to be, where the corresponding points match up there. If you have two equations, you can ask whether there's an ordered pair that is a solution to both equations simultaneously. And that's kind of our idea here. If you have two equations, you're saying, is there a point where it's a solution to both equations? Okay. The other thing that's to take away from this lesson, shown by the little race there at the end, is that when we have two linear equations that are equivalent to each other, like y equals 3x and that, then you get lines that are right on top of each other. And so any solution to the other one is a solution to the other. So you have infinitely many points, infinitely many solutions there when the equations are the same. Okay, so let's look at tonight's homework. All right, tonight's homework. It says Diego has $11 and begins saving $5 each week towards buying a new phone. At the same time that Diego begins saving, Lynn has $60 and begins spending $2 per week on supplies for her art class. Is there a week when they will have the same amount of money? And then how much do they have at that time? So let's make an equation for Diego. What Diego's doing is doing this. He starts with $11, right? That's his 11. And then he adds $5 a week by saving it. So he has his 11 and he adds $5 every week. For Lynn has $60 to start with, right? And then Lynn has her 60 and she's spending $2 per week. So we're going to be decreasing that $60 value by $2 every week. The point at which they're going to have the same amount of money is when these two things are going to be equal to each other. So let's set them equal to each other. 11 plus 5w equals 60 minus 2w. I'm going to go ahead and I'm going to add 2w to this side, add 2w to this side, so I have 7w, and I'm going to subtract 11 and subtract 11 so that I now have 60 minus 11 is 49. I get the w by itself by dividing by 7. And w is now equal to 7. So at week 7, they're going to have the same amount of money. How much money is that is the second part of the question. I could use either one of the equations and figure that out. So I could do 60 minus 2 times 7, just using Lynn's value there. And I have 60 minus 14, and 60 minus 14 is $36. So at week 7, they are both going to have $36, And Diego has that because he's saving money, and Lynn has that because she's spending money. And that's the place where they come together. If you were to graph that out, right, you'd end up with a graph going like this and a graph going like that. And the place where they come together is going to be that place where there's a 7 weeks and $36. And that becomes our intersection point there, or our solution to those two equations. Looking at number 2. Use the graph to find x and y values to make both y equals negative 2/3 x plus 3 and y equals 2x minus 5 true. Okay, so let's graph these out here. Let's first of all take the first one, and we're going to look at the first one here, and we'll do the 2x plus 3. So let's look at this guy here. I'll use a blue marker for now. What I look at is I start with my y-intercept, which is that number there, and I can put a point right here at 3 because it's going to cross the y-axis at point 3. And I look at my slope. My slope is going down 2 and over 3. So we can go down 2 and over 1, 2, 3. Put another point right there. Okay. I can do another one and go down 2 and over 1, 2, 3. Put a point there. And I go the opposite direction. I can go up 2 and over 1, 2, 3 to put a point right there. Okay. And that gets me where I need to be on that line as so. And then I can take my straight line here and we can make a little graph and we can make that work like so. And we have the line there for the first one. This is y equals negative 2/3 x plus 3. Okay, and now we do the same thing for the next one. Y equals 2x minus 5. My y-intercept here is at negative 5, so I'm going to start here. And our slope is 2, which means we're going up 2 over 1, up 2 over 1, up 2 over 1. And there's my intersection point, up 2 over 1. And I can do this all the way up the page if I wanted to. However you want to do that there. And then I'm going to connect the dots, like so. Okay, and this is my y equals 2x minus 5. Okay, and we want to find the x and y value that makes both equations true. And so in our case here, the x and y values is going to be this point right there, which is at 3, 1. So we would say 3, 1 is the solution to both of those equations, which is a nice way of saying if I plugged 3 into both of those, I'm going to get 1 as an answer to both of those too. Okay, so again, that's a graphing way. Here the first one was with an equation, and here we did graphs to show that those things are going to be true for that point. Alright, number 3. The point where the graphs of two equations intersect has a coordinate, y-coordinate of 2. Okay, so let's think about it like this. Here is a graph, right? So the point where two equations intersect has a y-coordinate of 2. So here's 1, 2. I'm going to just draw a little line like this. This is 2. So it crosses somewhere on that line. One equation is negative 3x plus 5. Okay? Alright, so negative 3x plus 5. I could graph that out and go 2, 3, 4, 5. Okay? And we can go over here 1, 2, 3, 4, however you want to do that. Because I know negative 3x plus 5, let's go here. Find the other equation if its graph has a slope of 1. Alright, well the one equation that I know, I have negative 3 plus 5. I know that it's going to start at the y-coordinate of 5, and we're going to go down 3, 1, 2, 3, and over 1. Notice here that with just that one slope going down one spot, I have a point here. That point is at 1, 2. Okay, that point there tells me where this first graph is going to go. This first graph, or equation, if I graph that equation down, is going like this. That's this one right here, y equals negative 3x plus 5. The other slope, it says, the other graph has a slope of 1. Well, I need to have a positive 1 from there, which means I can take this point and work backwards like I did in our lesson today. We can work backwards from there to figure out what that might be. Okay, so to work backwards from there, what we can do is we can say a couple things. We can say, we can go back and go, let's go, if the slope is 1, let's go the other way. We can go down 1 over 1, and we end up right here at the point 0, 1. Okay, for this guy right there. Knowing that I now have a y-intercept and I have a slope, I could use the equation y equals mx plus b, where m stands for our slope, and in our case our slope was what? Our slope was 1, so y equals 1 times x, and then plus rb, which is our y-intercept, which is here at 1, which is just going to be 1. So we could say y equals x plus 1 and leave it like that. And that can work for us, okay? If I wasn't sure about that point, I didn't want to draw a graph to get that point, what I could also do is I could do this. I could say that the y equals, using this equation, negative 3x plus 5. If I wanted to, knowing that I have a y coordinate of a 2, I could find this coordinate by plugging the 2 into there, right? Because whatever the x coordinate is going to be, that's a point. I can put 2 for the y coordinate and set it equal to this part here. And when I do that, what happens here is I subtract 5, I get minus 3 equals minus 3x, divide by minus 3, and you have 1 equals x. That's how I can also end up with the point 1, 2 located right here, right? So I can either just graph it out, or I could plug in one value to find out what that coordinate point is going to be. That's my starting point. And then from there, I could kind of work backwards with the slope to find out what the other equation is going to be, which is y equals x plus 1. Okay? Yep, and that's kind of what you can do there. The other way you could solve for this equation, in case you weren't sure here, here's one more way of doing this, right? If I know that I have a point y minus 2, I can also say that, remember, y minus y1 over x minus an x1 is going to be equal to the slope. Our slope was 1. So I know that to be true there. Now I have a point which was 1 and 2. So if I plugged in my points here like this, and we said y minus 2, x minus 1 using that point, and now I multiply that over there, we'd have y minus 2 equals x minus 1. And I want to get the y by itself, so I add 2 to both sides, and y is going to equal x plus 1. So that's the other way you could solve that. You can solve it using the point slope form, or you can solve it using this method here by looking at the slope they gave you and using one of the points that they gave you as well. Okay? Either way, you end up with the same solution. Let's take a look at number 4. It says a farm has chickens and cows. All the cows have 4 legs. That's a good thing. All the chickens